Welcome to our 6th week of the Catalysis webinar. Thanks to everyone for joining today. I'm looking forward to introducing our speaker from Forge Nano, Dr. Staci Moulton. Welcome you all. My name is Lorianne Schultz, and we also have on here Brian Ferrari. We're both from the American Vacuum Society at the University of Central Florida. And the way that this webinar is structured is that Dr. Staci Moulton will give a 30 to 45-minute talk. And if you have questions during any time during her talk, please go ahead and just type it into the chat box, and I'll collect those questions and ask them to her at the end of her presentation. And as I said, I'm really looking forward to introducing our speaker. Dr. Staci Moulton serves as an application engineer for business development at Forge Nano in Thornton, Colorado. She is a key liaison with customers and product partners for delivery of technical content, limitations of PALD, and market readiness of applications, including cost analysis. She received her BS in chemical engineering from Oregon State University in chemical engineering and her PhD from the University of Colorado, Boulder, studying ALD of cobalt for active catalyst materials, and her MBA from the University of Colorado, Denver. She was the PI for an advanced research projects agency energy project for ALD catalysis and its commercial opportunities, has authored ALD and polymer patents, and was a technology lead for a research firm proposing research projects to the US government agencies on commercialization. And today she's going to share a presentation on the basics of atomic layer deposition and particle atomic layer deposition for catalysis and the benefits to process intensification in chemical manufacturing. So I'll go ahead and turn this over to you, Dr. Moulton, for whenever you're ready.
Okay, great. And there it is. All right, so thank you, Lorianne, and thank you to UCF and the AVS chapter. I'm very happy to share what we're doing at Forge Nano, as well as a history of ALD for catalysis. And I'm really encourage people to ask questions here, but also reach out to me after this webinar or after you watch the video online after the event to ask questions to us, or I'd be happy to connect you with some of the research and other researchers in the area. So like Lorianne said, I have my PhD and MBA. I do focus on commercialization of technologies, so particle atomic layer deposition. That's what we do at Forge Nano, and making equipment for the commercialization of advanced materials. So my background is for to speed technology and what's possible for ALD and the commercial viability of those products and getting them out into the marketplace. Like it was mentioned, I was a principal investigator for an ARPAe project that was the application of ALD for catalysis, specifically in Fischer-Tropsch synthesis. I am going to mention a little bit about that today. I also went through an innovation core program for technology commercialization and have 10 years of experience in ALD on powders. So I'm really happy about this event and this webinar because I did a similar event with Forge Nano. I was the programming director for the PALD Summit, and we want to mention that the PALD Summit is returning in December of 2020. So this has all of the different applications. Catalysis will be mentioned there. And so we want people to go on, register for that event. We had over 900 people participate on our first event back in May. So we're looking forward to the second event. And so please go on, register, and come join us at the second PALD Summit. So the outline for today's presentation, I'm going to talk about what atomic layer deposition is, including particle atomic layer deposition. They're very similar, but slightly different in how you perform that work. Then specifically talking about catalysis and how is ALD useful for catalysis, specifically what's catalyst systems and reactions, what catalysts have been studied as well as recommend some research reviews and literature that is out there for you to go and look at more, and then come back, ask me questions. Like I said, I would really encourage you to come talk to me afterwards or ask questions here. And then focus in on what is commercially viable for chemical manufacturing with ALD. So hopefully by the end of this, you can see where the value is for ALD and catalysis. And really that's up to you, us at Forge Nano and researchers in the academic community and in industry to determine where that value is and then apply it. And that's what we want at Forge Nano. So Forge Nano, we're located in Colorado. This is actually a photo of our previous location just outside of Boulder. We've recently moved to Thornton, Colorado. We were founded in 2013. We are still a small business with fewer than 50 employees. We just moved to our new facility. It's about 38,000 square feet, which is only a portion of the entire facility that we're in. But our mission is to become a world leader in innovative material solutions. One of those application areas is in catalysis. Also, 2020 is a very exciting year for Forge Nano. One of our announcements is that back in February, we merged with ALD Nano Solutions, which was another particle atomic layer deposition company. So now we are the world's largest and most experts in particle atomic layer deposition. Also, we had to move facilities because we joined together both of our teams of ALD scientists and engineers and all of our equipment together. So we moved to Thornton currently. We're just closing down the Broomfield facility now. So a little bit more about us. We are an end-to-end material solution provider. So we have R&D equipment. We run particle ALD. We have about 16 different systems that we run. So we develop materials science around different applications, look at the scale up of those materials and the commercial viability of those materials with our partners and customers. Then once we actually determine that there is viability for that, we can go into toll coating, where we produce material for our customers in-house. So that can be anywhere from grams to kilotons of material. And our end goal is to sell equipment for large-scale commercial production. We also have lab-scale systems as well. So we are the world's partner for R&D and commercial scale-up for particle atomic layer deposition technologies. So get into atomic layer deposition and what is it actually? It's a thin film process where you're depositing material atomic layer by layer. It's analogous, or it's basically a bricklaying process. So you have gas phase molecules that come in, they react with the surface science, surface engineering, and lay down material. And they build up layer by layer in a bricklaying fashion. So those green and blue bricks are representative of molecules. So it's a very controllable process. If we look at this with actual molecules, this is a representation of aluminum oxide deposition. So it's a spontaneous gas phase reaction on the surface. So it's limited by the number of surface reactive sites that are there. It's a thermal reaction. There are other options that you can do, plasma and electron enhanced deposition techniques, but particle ALD should be mainly around thermal reactions. So you have a temperature window where you bring in trimethyl alumina in that first half of the reaction. It reacts with hydroxyl groups on the surface, produces methane. And then once all of those surface sites have reacted, you no longer have methane being produced, and you see the trimethyl alumina exiting from your reactor, as long as it's in a batch system. And then the second half of the reaction, you bring in water, reacts with those methyl groups on the surface, reproducing that hydroxyl group, and then you complete the one cycle, building up one atomic layer of aluminum oxide. I'm going to talk a little bit more about aluminum oxide actually for a catalysis application. So ALD has many different opportunities. Almost the entire periodic table is covered here. This periodic table comes from atomiclimits.com. This is a wonderful resource. I really do recommend going here if you're interested in ALD to see what has been done. For catalysis, some of the areas that are of interest is this middle part, your active material deposition, maybe titania, so your oxides. So for undercoats and overcoats, multi-metal oxides, mixed metal oxides are of interest here. You can also do organic or MLD or mixture of organic and metal oxide deposition to end up with a highly porous oxide surface. I'm going to talk about overcoats. MLD for overcoating is a really interesting application that there's been some work done at BASCAT in Germany with BASF. So there's a lot of opportunities here. If you're interested, again, please reach out to us. So particle atomic layer deposition, analogous to ALD, is basically the same thing. You're getting conformal, uniform, and pinhole-free films onto surfaces. Those could be spherical, non-porous particles. It could be porous materials that have trenches kind of like this, or just long pores, fibers, fabrics. There's a lot of different opportunities here. So this is what it really looks like once you get to the images. So that one on the left is a non-porous particle, conformal uniform coating, 5 nanometers thick. That's probably not what you're going to end up doing in catalysis, but the one on the right might be. And that's platinum deposition onto an oxide surface. And we'll talk more about which one of these, the left or the right, might be the most commercially viable application. But again, particles there in that image, that's what we focus on at Forge Nano. So in our R&D systems, when we do particle ALD, most of that is done in fluidized beds. So if you look on that right, the video is a fluidized bed. So you have gas flow coming up from the bottom. It's a rendering here on the left-hand side. You have a porous frit on the bottom that holds the powder within the reactor chamber. And then frits on the top to allow vapor to leave the reactor. You have the bed zone or the fill zone where you put particles, powder into the reactor. That expansion zone where you're reducing the gas velocity so your particles actually drop back down and stay within the reactor, including that disengagement zone so your particles will stay back down within the reactor zone. These are really efficient for precursor utilization. For ALD, we can get nearly 100% utilization and 100% coverage of the substrate surface in a fluidized bed. Again, so precursor utilization, we can have 95% utilization of a platinum precursor, which is very important if you are doing platinum deposition. Platinum alone is very expensive. Precursor is even more expensive. So the Prometheus systems are our R&D systems that we offer for sale for particle atomic layer deposition. One on the right, the left is the rendering. The one on the right is one of the systems that we have in-house for our R&D scientists to use. It's a very powerful tool. You can do a wide range of chemistries. You can do a wide range of sample mass. So you can go anywhere from milligrams up to a kilogram of material production in this system. The fluidized beds are not the only thing that we use for particle ALD. So staying within the batch realm, we also do rotary reactors. There is a rotary Prometheus version, as well as Lithos, which is a larger scale batch ALD reactor. So this vessel rotates and to coat the material. There's some advantages to that for flexibility in how thick you're depositing that coating. And there are, although some disadvantages in that system, which is why we have so many different kinds of systems. So in this, we can go up to 200 kilograms for a demonstration. You can see how large it is right there. And we have designs to go even larger than that. And I will review our different systems again at the very end of this. So moving from batch, because at Forge Nano we focus on commercialization of materials. So if you're going to be producing thousands of tons or millions of tons per year, you need to go to very large production pretty quickly. So we use the batch systems for development of materials. We prove out their usefulness, and then we go up to our continuous production to get the economics of that production. So CIRCE is one of our continuous production ALD systems. This has substrate moving horizontally on a vibrating bed, and we can get to 3 tons per day production throughput on this system. It currently exists. So this is really fun. I like showing this video. If you like this portion of my talk, please go to the AVS ALD 2020, and our VP of R&D, Marilyn Dameron, gave a talk about all of our different systems and went in depth of how they work. So on this continuous vibrating bed, the powder moves along and it goes through those different zones right there. It's going through an exposure zone to the different precursors. And again, this is like this is an aluminum oxide deposition. So you have trimethyl alumina and water. That powder just moves along and goes through about 3 different cycles and it gets to the end of the system, and then that powder is collected. So this is just a little bit slower video showing that powder motion. So this is fun. This is what we do. This is what we focus on at Forge Nano. So the R&D of the application space, we work with customers, but we can get to the commercialization, full-scale production of that material. So one last system is our semi-continuous production systems for particle atomic layer deposition, and this is Morpheus. So rather than a horizontal moving on a vibrating bed, this is using gravity and pneumatic transport to move powder vertically through different systems to get the cycles needed. All right, so Forge Nano, we work on particle atomic layer deposition. There are many different opportunity spaces for this. The first one is in energy storage, where we've had the most success. Our second is in catalysis, which I'm going to talk about today, point out some of the references, the review papers, the opportunities that have been explored, and encourage people to continue to look for other opportunities. Other application areas are thermal fillers, powder forming or 3D printing, separations, so adsorbents, and membranes. And then as you go around, we've worked in almost all of these application spaces. The top 5 are the main ones that we're focusing on, but we absolutely work in most of these. And if you have some ideas, please reach out again. All right, so now we're going to switch over to talk about ALD for catalysis specifically, giving you all the background about Forge Nano and where we focus on commercialization. So this is some of our data for BNOX catalysts with an overcoat. So I'm going to talk about the 3 different ways that we see ALD being useful for catalysis. One of them is overcoats. So having an oxide deposited on top of your active catalyst material. The images over here on the left are showing a comparison of a ceria deposited onto a catalyst, and then this is zirconia deposited. So it's not the same material, but the main point here is to get the point across that ALD will be uniform everywhere on the surface compared to sol gel, where you will get some clumping. So you can see a little bit more of that pink clumped around and not as uniform deposition as you get on an ALD with an ALD catalyst. And then on the right, that performance, the goal of catalysts is long-term stability. When you make a process, you want to ensure that you are going to have consistent performance day in, day out. It's not going to shut down unexpectedly And that's where you get your best economics. So designing your catalyst to perform consistently is one of the advantages for ALD. So an overcoat can maintain the performance over a longer period of time than without having an overcoat on your catalyst. There are also some other benefits that we'll talk about. So this is my viewpoint of saying that ALD for catalysis can basically be like a treasure map. There are opportunities out there waiting to be found, and I'm encouraging people to go find them. So ALD has been used for fuel cells, for hydrogen production, for dehydrogenation and hydrogenation, photocatalysis, methane reforming, biochemical conversion. I'm going to also talk about Fischer-Tropsch, which is what I did my PhD on. So there are other opportunities out there waiting for ALD. In the ALD toolbox, this is what I was mentioning. So we have overcoats, where you typically an oxide, but it could be some other material, mixed metal oxide maybe, is deposited on top of the catalyst that's made in a standard method, maybe incipient wetness. Or you have the active material deposition. So you can use ALD to deposit platinum, palladium, rhodium, ruthenium, cobalt, or you have undercoats. So you can deposit an ALD layer, maybe a mixed metal oxide or an oxide, onto the base support, and then use a standard method like incipient wetness to deposit your active material, or use a combination of ALD methods to build your catalyst from the bottom up, which I'll also point out. So the benefits you're looking for in catalysis are the durability, long lifetime, having a higher selectivity and higher yield to the desired product so that you have less separations in your processes and more energy efficiency. And then activity, which will also increase yield of the desired product. So as I mentioned in my title, this process intensification is a goal of chemical manufacturing so that you will have lower energy usage and higher production of the most desired product. You can get there by increasing your selectivity and your yield, decreasing the amount of separations that you need to do in the process. So I'm a chemical engineer background. Process design and process control is part of what we think about when we're looking at catalysts. So I'm going to point out 6 different review articles here that I recommend people go look at if you have not looked at them before. The first one is with Jeff Elam, Neil Dasgupta, and Fritz Prince. They're 3 great experts in ALD. Jeff Elam is a great colleague of ours at Forge Nano. He recently purchased a Prometheus system, so they have that at Argonne National Lab for some of the development that they're doing. The next one is this catalyst design with atomic layer deposition. It was published in 2015. Another great reference for all of the different things that have been done with ALD and catalysis. Here's another one with Jeff Elam and Peter Stair at Northwestern, and Junling Liu, who also has another review paper here and a lot of background work for ALD and catalysis. So bottom-up synthesis, I mentioned that before, and we'll talk about that again. This nanoengineering of heterogeneous catalysts with Staci Moulton. So this was from Stanford. And this review article for catalyst design via selective atomic layer deposition and atomic scale engineering of metal oxides for interfaces. So again, with Junling Liu. So there's 2 reasons to do ALD for catalysis. It can be as a tool for fundamental science, which typically will not make it to industrial processes, and then industrial processes. So those 3 different ways of doing ALD in combination for ALD catalysis are the active material deposition, the overcoats, and the undercoats. In our opinion at Forge Nano, the active material deposition is still a great tool for fundamental science, but it is not yet to the point for an industrial process. Whereas the undercoats and overcoats are much closer to an industrial process, having nano-level control at an industrial scale. So there are opportunities here, though, to blur the lines and bring some of those undercoats and overcoating technologies back towards fundamental science. And with time and effort, there will be opportunities for that active material deposition to transition to being an opportunity for an industrial process. The fourth thing that I want to bring up here is area selective ALD, where you're controlling where maybe your active material is on the support. And that has an opportunity to become an industrial process if you can increase the selectivity. So active metal deposition, this is some work that we did at Forge Nano for palladium deposition in comparison to a baseline, like an incipient wetness deposition. So this histogram here is showing the particle size distribution. So ALD will get you very tight, narrow distribution of particle size, but the incipient wetness can do really well at this. So there's some added costs that may not benefit enough to need to do ALD of the active material of platinum or palladium. So some areas where theory can become reality and may actually be beneficial are these core shell structures. And here's an example. So with palladium and platinum core shell materials, that deposition of the metal will actually preferentially go to the metal surface. So your energy differences, materials will always go to the lowest energy state. So sometimes you can selectively deposit material where you might want it to form these core shell structures. So these two examples in the bottom, so this is from one of those review papers. You can have an oxide that's different from your support oxide, which can change your selectivity. You can deposit around the material. And again, this all goes to what you're depositing and what you're depositing onto. The combination of those things going to the lowest energy entropy state point, that's what you're going to get. And then depending on what conditions you take it to. Over here, this is an overcoat material and actually showing that overcoat on the palladium. So bringing those back right now, core shell structure, great fundamental science. It may not be industrially relevant yet. Overcoats, those are getting much closer to being industrially relevant catalysts. So the area selective deposition, this was in the review paper, as well as here's the reference to the original work. So this is taking pristine graphene, making some oxide sites, and then depositing palladium onto those specific sites. So you can get almost a single site palladium reaction. The opportunity for this is high selectivity. So you can get high yield to a single desired product and eliminate secondary reactions in your stream. So this will improve your overall process economics and potentially be an opportunity for commercialization. I said on that ALD treasure map for catalysis, photocatalysis. So this is a bottom-up synthesis. I'm taking carbon nanotube and doing a complete ALD processing, deposition of platinum, titanium dioxide, then removing the carbon nanotube and depositing cobalt oxide. All in ALD steps, and then looking at the hydrogen evolution. So you can get really interesting, great results with ALD, and every step being ALD in a bottom-up synthesis, but that may not be economically viable. And so that's something that we look at Forge Nano. So I'm going to review my own work. My last name was Van Norman. This is from the University of Colorado at Boulder, where I did Fischer-Tropsch synthesis with an ALD catalyst. So it was a cobalt deposition. It was metallic deposition of cobalt. So background on Fischer-Tropsch synthesis, it is a structure-sensitive reaction. So your yield of product or your conversion of carbon monoxide, Fischer-Tropsch synthesis takes carbon monoxide and hydrogen and makes synthetic oil. So if you look at that conversion of carbon monoxide per amount of cobalt, you have a peak around 7 to 10 nanometers on everything that has been shown for the last 100 years of research in Fischer-Tropsch. In comparison to ALD and increasing the number of cycles of cobalt deposited in a metallic method, so that was cobaltocene and hydrogen. With one cycle, you're within the same turnovers or yields per cobalt here that you would get for a normal Fischer-Tropsch synthesis catalyst. But if you increase those numbers of cycles to 4 and 8 cycles, we're much higher than anything that was ever reported before. In fact, it's 3 times higher than the highest efficiency at a similar conversion of carbon monoxide and selectivity. And that's important to be selecting points that have conversion and selectivity similar so that we're not comparing erroneous points. So like I said, we're making synthetic oil from carbon monoxide and hydrogen. Mainly it makes a lot of water. Really, they should call it a water production reaction. So again, this is that same data. So it's a structure sensitive reaction. Once you get up to 7 to 10 nanometers, the turnover frequency stabilizes. You're not using any of those other cobalt atoms that are interior to the particle. So again, if we bring in the ALD data, the one cycle catalyst looks like it's very, very small nanoparticles. And in fact, they're around 1 nanometer, which is kind of what we would expect. But if we look at the 8 cycle catalyst, and here's the error bars, we're much higher than anything, a turnover frequency than you would expect to see. So during my PhD, towards the end, we looked at some other studies that actually looked at single crystal comparison. So they took a tungsten single crystal in an ultra high vacuum chamber, deposited cobalt as a metallic onto that surface, and then transferred it over to a reaction chamber and looked at the turnover frequency with increasing temperature. So when we plot our cobalt ALD catalyst on here, the 1 cycle is very low turnover frequency that we expect for very small nanoparticles. And the 8 cycle cobalt is up here within the error. These are the error bars for that turnover frequency study. We're within the error of their turnover frequency. So it appears that the cobalt was depositing more as a single crystal form. And what we saw on the surfaces is that you actually have very small nanoparticles, but you have these crystalline surfaces as well. So it's likely that some of the cobalt was depositing as a single crystal on that support. Okay. So I'm going to transition now to undercoats and overcoats. When I was at the end of my PhD, I was doing an ARPAe project. We actually looked at the commercial viability of that Fischer-Tropsch synthesis reaction. What we determined is that even though we improved the Fischer-Tropsch synthesis, the syngas production was not viable, made the entire process not viable. So I'm actually going to highlight here where dry reforming of methane can be improved by ALD. This is this paper from the University of Pennsylvania state. But here's the reference. So it has a calcium titanate ALD layer and a nickel deposited by incipient wetness. So same nickel deposition on both, just an ALD layer here. So the ALD, when exposed to methane, did not have this carbon nanotube or carbon whisker formation, which on a standard catalyst in dry reforming of methane you will have the nickel actually pushed off of the surface, and you will react so much that you fill up your reactor with carbon nanotubes or carbon whiskers that it will plug the reactor. With that ALD undercoat, you can actually shut off that coking formation and be able to operate consistently without carbon formation. Without that, you have a consistent carbon formation until you plug the reactor. And what that looks like are these carbon nanotubes here without ALD, and here is with ALD. You do not have that carbon nanotube formation. So an overcoating, this is a platinum catalyst. This work was actually also done at the University of Colorado Boulder by Zhenhua Yang, 2011. I was there, I know him well. So you have a platinum catalyst with an overcoat here, an aluminum oxide overcoat, and then without an overcoat. And he took those different catalysts, 6 different catalysts here, and exposed them to increasing temperatures for 4 hours and looked at the sintering of the platinum. So you can stabilize your platinum by having an overcoat. So you can reduce the amount, because over time, if you're going to operate at 600 degrees Celsius, you have to have more platinum there to have the same activity at the end of life than you would if you have an overcoat on the material. So another example with overcoats here, this study in 2012. And at Forge Nano, we actually are doing similar work to this. So you have a palladium catalyst, then an overcoat, again, of alumina. And they make these micropores by cracking the overcoat afterwards to allow exposure to the catalyst. So this is oxidative dehydrogenation of ethylene. And so it has the initial without the overcoat levels here, and then you stabilize the production over time so that you can perform much longer, as well as a higher selectivity. So as I mentioned at the beginning and in the title of this, the process intensification is increasing selectivity and yield, as well as increasing your durability of your catalyst. So this is a really great example of ALD increasing your process intensification and as a industrially relevant application. And actually we are working with commercial partners. So this is now work at Forge Nano with partners that we've worked with at Pacific Northwest National Labs, at NREL, specifically Amy and Derek there, and Johnson Matthey. So this was a biochemical conversion, so meconic acid to adipic acid. Over here on the right is the publication for bio-based adipic acid. So we did an overcoat of 5 cycles of alumina onto a palladium on titania catalyst. One of the questions is ALD uniformly deposited throughout a porous structure? So this data here is showing that the alumina throughout a porous structure is depositing uniformly. As long as you are operating within an ALD window and you let it run to completion, you will get deposition everywhere. That's how ALD works. So here is some of the data. So this is for the regeneration and reuse of the catalyst. So that blue decreasing data is a fresh catalyst without an overcoat. And here is no overcoat and after 5 thermal treatments or regeneration. So you have a significant drop in that conversion or your productivity of the catalyst over time after you regenerate it. And these blue, green and orange is a fresh with an overcoat. And after those same 5 thermal treatments, you have the same conversion over time. So that is being able to maintain your catalyst with your regeneration is one of the benefits of overcoats. So the other benefit here for this example was that we could actually stop leaching of palladium off of the surface. This is a very big advantage as well, so you're not losing your active material to the process. And this is the same study, same work, these thermal treatments at 700 degrees C. So this is showing similar to Jinhua Liang's work with platinum, except this is for palladium and showing the sintering. So 700 C for 4 hours, palladium sinters without an overcoat versus with an overcoat. You maintain the dispersed palladium on the surface. And because you're maintaining that dispersion, you're actually maintaining your reactivity. Final study work that I want to point out that we're doing at Forge Nano is an overcoat on platinum. So this one is a little bit interesting because we're doing aluminum oxide overcoats onto aluminum oxide support. It's a little bit of a complication that you're depositing A onto A, but there actually is some difference between an ALD aluminum oxide versus a support aluminum oxide. We hope to have some of that information ready to share. That publication will be out soon. Our partners on this work are Zhang Liu at Argonne National Lab and Lee Abrams, primarily Lee Abrams at UOP, and that's an Advanced Manufacturing Office funded project. So I'm just gonna reiterate again, for Forge Nano, we focus on commercialization. So we sell equipment, we encourage people to be developing ALD technologies, not only in catalysis, but that is one of the application areas I'm excited about. So we sell tools like Prometheus for people to do research and develop technologies so that then they can come back to us and we can scale it in systems like Morpheus or CIRCE or Lithos. So all of our equipment that is available, so our lab scale systems, I mentioned Prometheus. We also have Athena, but Pandora, the official product release, will be coming out very soon. If you're interested in commercialization, there's some opportunities about Pandora that we'll be announcing. Please reach out to me about that. And then our commercial scale systems, Lithos, Morpheus, and CIRCE. And so at Forge Nano, we have the world's experts in particle ALD in the commercial systems to back it up and the commercialization programs.